All right. So here today we're going to be doing our 9.3 lesson. This is one of these lessons that if you're just watching the video notes, it's probably just more for a review or just like a walkthrough of how to do all the things. Some of these numbers are just going to come out of thin air, and it's because in class we did an experiment where we actually tasted the rainbow and ate some Skittles. So what we're doing in class, or what we did in class, depending on where you watch this, is your group is getting like 20 or 30 Skittles, and you're taking a random sample of five. And someone's going to see if they can taste the difference between the colors. So, and that'll be important here when we set up in a second. Now, this collect class data, this is not something you would do on your AP exam because it would tell you already. But as an example, I tested a class and they got 97 correct out of 150. It's going to be different depending on every class, depending on your notes. But this is just one example. What we're going to do is we're actually going to perform a significance test, and it still uses the same 4C method for inference. It's designed to help you remember all of the details that should be included, and it ensures that you will get full credit for any inference FRQs. And I know there's a lot there, but the reason I do it is so you know you'll get full credit if you do the things. Now, I've already filled in some of this here just to help us out a little bit. The first C is choose. You choose the inference procedure, set it up. Our procedure here is a one sample Z test. You will notice the difference here is this word Z test. From when we did intervals, it was Z interval. Now we're doing a significance test, it's Z test for P. Parameter, the true proportion of correct guesses for all Skittles. Our statistic, our P hat, we do actually want to list that here. Confidence intervals, you don't have to list it. Here we do want to list it. That way we know we have it at the top and we can refer back to it later. Finally, you do want to list the significance level. Similarly to a confidence level, the problem will tell you which level to use. You still have to list it. Treat it as if they don't get the prompt at all and they're just reading your work. So still list it. Last thing we have to do is list our hypotheses. Now, this one here, I think these can be a little challenging. Remember that our null hypothesis is what we assume to be true. In this scenario, you took five Skittles and you tasted them. If you are randomly guessing, there's five flavors in the Skittles. So a little fun fact for you, there's five flavors in Skittles in a Skittle pack. If you're guessing, we should expect you to get one out of every five correct because there's five flavors. That gives us here that our null hypothesis should be 0.20. It's what we expect, what we think, all of those things. So we expect one out of five correct, 0.2. Now, what that means, if we can actually taste the rainbow, our or our alternative hypothesis, if we can actually taste the rainbow, means that we would be greater than 0.2. You would be getting more than 20% of them correct. And we do actually have some evidence for that. What is our evidence for our alternative? Well, it's that our sample is 0.647. That's greater than 0.20. So we do have some evidence already. That doesn't mean we're just done with the problem. We still have to do our full inference procedure and actually make a conclusion. So that's our check or our choose. Our check. It's the same thing though. We have to do three things. Is it random? Do we follow the 10% condition? And do we follow the large counts condition? Let's start with random. You're taking a random sample of Skittles and then you're blindly tasting them. It is a random sample of Skittles. Meaning, yes, we can do what? Generalize to the population. Cool. One thing down. We can say generalize to the population. You could also say here to all Skittles, right? Um, More context, better. To the population's cool. 10%. Now, here we want to look at our class data. In my example, 150 was our sample size. That is reasonable to assume it is less than 10% of all Skittles. I don't think anyone would fight me that 150 is less than all Skittles that have ever existed. Now, why do we care about this? So, sampling without replacement is okay. Cool. Next, large counts. Now, this is where it gets interesting. If you followed along with 9.2, we um, we talked about this. You don't want to use p hat here. We want to assume that our null hypothesis is true, meaning we're actually going to use p when we do the large counts. And we'll put that note off to the side. But what we find here is that 30 is greater than 10. And here we find 120 is greater than 10. These both check out. And that allows us to say that the sampling distribution of p hat is approximately normal. And again, just so we have it, we're going to add in here with some stars that we're going to use p, not p hat, similar to what we did in 9.2. Okay, through the choose and check, obviously slightly different. It's a Z test. We have to list hypotheses and a significance level. The checks are roughly the same. The reasons are the same. We are only, it's a different procedure because we're dealing with significance tests instead of confidence intervals. The calculate is where it gets a little interesting here. Um, so our conditions are met. We have 6 things we have to show. Now, the general formula, this is talking about a test statistic. This comes from 9.2. It's statistic minus parameter divided by the standard deviation. Even after we come back from spring break and we're in the world of means, will be that way. The specific formula here, it's a test for Z, so that's why our test statistic is Z. And because it's a one sample Z test for P, our statistic is P hat, our parameters P, divided by the square root of P times 1 minus P over N. Again, as a reminder, here you're using P, not P hat. Then you just plug the numbers in. You actually have all of these numbers. Z equals 0.647 minus 0.20 divided by the square root of 0.2 times 0.8 over 150. Now we plug this all in, we get 13.68. That's our test statistic. So we can actually fill that in right here. Now, one thing we have to do is we actually need to draw in a picture. The picture is going to be your normal distribution. And good practice, we're always going to label. So with our mean and our standard deviation, which is 0.033 standard deviation. Okay, we draw in our mean. Now, what we're trying to do, we're trying to test this value right here of 0.647. What's the probability of getting that purely by chance? Now, we do this because we can now use Desmos. In fact, this one here is an example. That z-score of 13.68 is so large, you can't do it without Desmos or your TI-84. The table A doesn't work for this. So we can actually, though, go to Desmos and check this. So 0.2 is our mean and 0.033 create a distribution. We're looking to the right of 0.647. What you're going to see is, first of all, 4.2 times 10 to the negative 42. Really small number. In fact, I have to go quite a ways out, and then I really have to zoom in before you're even going to start seeing shading. In fact, it's not even letting me zoom in anymore. What that tells you is our p-value is pretty much zero. In fact, this really, if we were to draw this better, like we can, we'll try to draw it better. It's like here, and there's like nothing, right? We just put it here just so we can actually show that we look to the right of this value. We did all of this calculating. We have our p-value of 0. Now, when we conclude, we have two things we have to do, and it almost builds a paragraph. The first thing is we interpret our p-value. Assuming our null hypothesis is true, our null hypothesis is 0.20. There is a approximately 0, and I should probably use English, right? And approximately 0 probability of getting p hat of 0.647 or greater purely by chance. Now we're going to step away from stats brain for a minute because we still have to make a decision and conclusion. Basically, what we're saying right now is that the class isn't guessing. They can actually taste the rainbow. So for us, we know that okay, we're not just guessing. We actually know. That can help us with our decision. Now remember here, our decision starts with because our p-value, which we're just going to say p-value for our sake, is zero. It's almost zero. But because zero is less than 0.05, which is our alpha value, we are going to reject our null, and we do have convincing evidence that the class can taste the rainbow. And we'll give a little bit more context here, um, and say that we do have evidence this is the case, that p is greater than 0.20. So here, the first thing, interpret a p-value. And then the next thing we do is make our decision plus our conclusion. And we say with context. So that's our whole thing from choose, check, calculate, conclude. Now, let's summarize this all up because there's a lot there. And this is just one example. The 4C method. There's a lot of stuff here, and we're going to get to this two-sided in a minute. Don't you stress. Let's just look at this for now. 4C method for inference when we're doing significance tests for a proportion. Now notice, for a proportion. In our choose, we state our procedure. It's a one sample Z test for P. Right now, if that's what you want to talk about, and you want to say, hey, this is a one sample Z test for P, cool. Alpha value, it'll be given to you. Parameter, you state that. Statistic, it's your sample proportion. And your hypotheses. You need to make sure that you state both the null and the alternative. You have to state both. You check your conditions and you say why. Why do you care? That should be feeling pretty normal now. It's third unit in a row we're checking these. Calculate. General specific formulas. You plug in your numbers. What's new here? You have to show the picture. Now you have a picture. Because in order to get this p-value, you need to show your picture. So these two kind of go hand in hand with each other. And also the test statistic, you do need to show that. You do have to calculate the z-score. You do have to show the z-score. Finally, conclude. You have two separate parts. It creates almost, I'm going to call it a paragraph. It's a two-sentence paragraph. Interpret your p-value. Assuming our null hypothesis is true, there's a blank probability of getting a p hat of blank or greater purely by chance. Because it's our alternative is greater, we're looking at that. If we were looking at our alternative being less than, it would be blank or less than purely by chance. Then our decision, because our p-value is less than alpha, we reject our null, and we do have convincing evidence of our context. What I want to point out here, and we're going to get to this eventually, but it's here right now. You have a two-sided, you can have a two-sided, basically where our null hypothesis is one thing, and then our alternative is just that it's not the null. Again, this one here, the context really matters because we don't really care if we're less than 20%, because if we're less than 20%, we can't taste the rainbow anyways. So that's why this is just a one-sided. Two-sided, you would see when you do all your stuff, you would have two areas you're looking at, which is why the p-value is area times 2. We'll get to that. That will be a thing. We'll talk about it. This is not as important to us right this second. Okay, I highly suggest you see all of this blank space. Do the significance test. This is actually a really interesting question. Hint, hint, this is a really, really interesting question. Hint, hint. All right, guys. Good luck with your studying. Hopefully, this helped. Peace.